We know that momentum is an object's mass times an object's velocity. Calculating something's momentum is not as important, however, as looking at how momentum is conserved. The conservation of momentum is one of the big principles in mechanics, in physics. And the conservation of momentum principle says that if no net external force acts on a system of particles or objects that can be treated as particles, then the total linear momentum of the system cannot change. Another way of saying this is that the total initial momentum of the system is equal to the total final momentum of the system. You can find these total momentums of the system by adding up as vectors the momentum of each object that's in your system. And again, we're talking about systems of either particles or objects that can be treated as particles. Now, when we're dealing with conservation of momentum, we'll often talk about collisions. There are 3 types of collisions. Each have their own unique properties. You need to know what those 3 types are and what makes them special. We'll start off with the first type being elastic. In elastic collisions, both the kinetic and potential energies of our system are conserved. Kinetic and energy and momentum of our system are conserved. Remember, it's the kinetic energy of the system that's conserved, not of an individual object. In inelastic collisions, only momentum is conserved. Most collisions that we see are inelastic. It's very rare to actually have an elastic collision because any collision that contains sound of any sort would lose energy. Therefore, kinetic energy of the system cannot be conserved. Completely inelastic is one more special type. Now, you may also see this referred to as perfectly inelastic, but the AP board likes to use the term completely, so we'll stick with that. And in completely inelastic collisions, your 2 objects have the same final velocity. So in other words, they move together as one object after the collision. So let's take a look at an example of a collision. We're really an example of a situation where momentum is conserved. We have a 4-kilogram object sliding on a frictionless surface, and it explodes into 2 2-kilogram parts. One of them is going at 3 meters per second due north, and another one goes at 5 meters per second at an angle of 30 degrees north of east. The problem is asking us to find the original speed of the mess kit. So if we're thinking about this, we have 2 objects at the end, and we start off with only 1 object. And conservation of momentum says that the total initial momentum is equal to the total final momentum. So in the beginning, we have this 4-kilogram mass. I'm going to use that as a capital M to be the mass of the big thing, times the initial velocity of our original object. And that's equal to the mass of a smaller part. Since the 2 parts are the same mass, I'm just going to use a lowercase m, times the final velocity of one of them, plus again that little mass m, times the final velocity of the second one. Now you'll notice that these are definitely vectors. One of them is 3 meters per second due north, and the other one is 5 meters per second at an angle of 30 degrees north of east. You can choose to handle this 2 ways. One method is to put these in unit vector notation and then add your vectors together. Another method would be to break this up into components. So focus simply on the x component first and then on the y component. Whichever method you prefer is totally fine. Your task now is to continue this problem and find that initial velocity of your whole mess kit. Remember, this capital M represents the mass of the entire kit, or 4 kilograms, and these lowercase m's represent the mass of the 2 2-kilogram parts. Your task: finish this problem and bring your answer to class with you.